moment. Oops. All right, and let's roll together, okay? If you enjoy adding details in your proposal, you probably have enough room, but for the examples that we're going to do, we're going to run through more examples, so I would encourage you to write this on a piece of paper, or do not encourage you, do not encourage you to squeeze it between the lines. These are, this is what we're working from today, the lecture note sheet provided. Okay, so quick reviews, in that one of the first flaps, wherever you put Q equals MCAT, Q equals MCAT is a way we phrase it. Of course, there's no A in that formula. But SDs, what does C stand for? And what kind of units are we dealing with specific heat? More than that.
Grams, Celsius.
Joules, right. So what's weird, think back to the R constant we used in the ideal gas law. Remember that one had a bunch of units together, atmosphere, liters, moles, and K? That was Kelvin. In Thermochem, we are not using Kelvin. We are using what? Celsius. So it's very specific. Gases has to use Kelvin because that's what the kinetic molecular theory stands or tells us to do. And then in Thermochem, we have to use Celsius. So that's one change here. Also, now we're talking about Q, which is measured in what unit? Joules, because that's a unit of heat. How do we measure heat? What's the tool we use in the lab to measure heat? Thermometer is not going to measure heat. Does that measure in joules? What is the thermometer measuring? Celsius or Fahrenheit or maybe Kelvin. Say again? I know, I did out loud, didn't I? Okay, so how do I measure heat? You drew a picture of it. Say again? Calorimeter, right. Calorimeter. That was like the styrofoam cup example. You had like a cup and you put stuff in it. I mean, that was on your, one of the second flaps that you drew. Okay. So we have to measure heat in a very specific way because heat is very hard to contain. We don't have specific instruments that just like, oh, well, yep, measure this. That's going to have 100 kilojoules or 100 joules. We don't have anything like that. So we actually have to derive it through calorimetry and calculations. That's the calculation. M stands for mass, so it's going to be in grams. If I give you moles, you have to go to grams or vice versa. C is in joules per gram degree C. Okay, so we're seeing some continuity here. And T, or delta T, is measured in Celsius. What units cancel on this side of the equation? Grams on top and bottom, and Celsius. Yay, joules is what we're going to be calculating. So we always want to make sure we're writing units down because they do get pretty specific here. So we're going to do another question with this one. You guys did this one on the video. You with me? Remember this one? Okay. So you actually solved for the C value, the specific heat capacity. We're going to solve. So do you guys see where this is on lecture notes? It should, I don't know which side the front side is anymore, but it's the one that says lecture notes and practice. So check, we've already done number 1. Let's do number 2, but I will say that sometimes I give you the specific heat capacity in the text or in the questions, sometimes I don't. So let's see what we need here from NLO, because I have to provide you maybe something here. So same thing, we always list out all of our variables, then we choose the equation to utilize because the variables tell us to use it. So question 2, how much heat is needed to raise the temperature of 40 grams of iron from 20 degrees Celsius to 40 degrees Celsius? Bailey's table, give me one variable that we know. Okay, so what variable is that? M for mass, right? So M is equal to 40 grams of iron. Okay. Bryce's table, give me another given. So what does that help us achieve? What variable? Okay, so how do I calculate temperature change? How do I calculate delta T? Right, we have to do final minus initial because that's going to give us the correct sign, either positive or negative. So T final minus T initial is what, 40 minus 20? So I know we can do that. That's 20 degrees Celsius as our overall delta T. Give me something else that's maybe provided, SD's table. What other kind of information is here? You're looking for what variable? Q. Our question is Q. And if you want to write down joules, you'll at least remember that the unit is specified. So in a textbook or in a table, what you would have to look for is what? C. And I think I'm here, iron. It's probably hard to see on this brown background. but it says iron is 0.450. Oh, sorry. Yeah, 0.450 specific heat capacity, okay? Joules per gram degree Celsius. Iron is 0.450. Write that down. Joules per gram degree C. Okay, so if we have the question of Q, we're given M, we're given delta T, and we're given C. Ryan's going to pass out the calculators. He's walking around with the calculator box over there. You guys tell me what equation comes to mind. The first one we use, which is Q equals MC delta T, or MCAT. And that's actually arranged the way it should be, because if we're looking for Q, we're solving for Q. We're going to plug everything as is. 40 grams, put your units, 0.450 joules per gram degree C, and 20 degrees Celsius. That's the Celsius. What are the units that cancel for me, guys? Grams, top and bottom, and Celsius. So we're left with joules. I'm ready when you are. 360, just no decimals on the dot. Can I get a second on that? Okay. And here's our final answer. So basically what we answered or we described is an internal heat change. And that's like sometimes hard to understand what's happening, but if you have a piece of metal like iron and you apply this much heat, like from a stove or from a hot plate, what you should understand or what you should see is that if you had a thermometer on that piece of metal, what's going to happen to it? Say again? How many degrees Celsius? Well, no, if I apply this much heat to the 40 grams of that metal on the hot plate, it should go up by 20 degrees Celsius. The thermometer is going to show 20 to 40. So we could set up the scenario in the lab and actually do it. Okay? You guys have a picture for that one in your book, in your folder already? All right, maybe you can like just draw what I just described, or maybe you have another scenario you can draw. Make sure that part of the folder is complete. What should be in it? I'll review that one more time. For these the following bullets here, the description, which is the notes, like the like one sentence of notes that you guys get written there. The definition of the variables, including units, which is I kind of just reviewed that with you, and then you have a diagram or some sort of illustration that helps you either remember the equation or remember the scenario in which you should use this. Effective use of color. It's always helpful. All right, I'm going to take this down. I'll show you it on my website later. Okay, and if you are able to, actually, I think we'll move on. Do you guys get how to use people's impact? Provided the variables here. You feel good about people's impact? It's a yes or no, people? Yes. Okay. All right, so let's look at calorimetry. This is the fancy calorimeter. The calorimeter, the one that was wherever you wrote Q is equal to negative Q, that is the flap we're on now. Okay, and so it's called calorimetry because it's dealing with calories. Well, if you ask the normal person on the street, like, what's a calorie, what would they say? What would they say? They would just like, hey, I eat calories, but what is a calorie? Talk in your groups what a calorie is. Alright, Maverick's table, what's a calorie? It is just a unit of energy, just like a joule is a unit of energy. I don't know if you guys wrote this part down. Do you guys know the relationship between joules and calories? The numbers that 4.18 what? 4.18 joules is equal to 1 little c calorie, lowercase c. Because what they do, and I've told you guys this before, they lie to us on our FDA labels. They say, oh, a banana is about 100 calories. They mean big C calories, which is a kilocalorie. So a banana actually has 100,000 calories in it. You heard me, 100,000 calories. But that's little c calorie, which would be 4 million joules, right? No, 100,000. 400,000 and some change joules. So there's a lot of energy in the food we eat. There's a lot of energy that people don't understand what it does. Basically, you use it, and if you eventually burn it, you breathe it back out as carbon dioxide. The more you breathe out carbon dioxide, the lesser mass you put on. Okay, so this is the structure of the device that we'll use in our lab on Wednesday. We have another lab we're going to do tomorrow where we're burning food to actually indicate the energy found in that food. So you'll see in your homework on the website it says bring in a small sample of food. Okay, we are going to burn the food and we're going to see how much energy is transferred in that process. So then we can calculate how many calories are in our food pieces. Like a little bite. Like, don't bring me a bagel, okay? Bring small pieces of food. If it doesn't burn well, I've got backup marshmallows from our smorikometry lab. But the idea is that you're going to burn something that you would eat in everyday life and maybe be able to calculate the calories from that personal object. So we have these styrofoam cups. Why do we use styrofoam? Because they're great insulators, right? So we have like an exchange of heat going on the inside of the coffee cup calorimeter. We literally use just styrofoam coffee cups. So we have a heat exchange going on in here. We can keep the heat in there. We can measure the changes that are occurring versus it being, released through the styrofoam. So the styrofoam is a great insulator, which helps us get very good results in the lab. Very good. Questionable results sometimes, but okay. So you guys did this one, yes? Check. Okay, so that's the next one on the sheet. Okay, so we did this one. Now we're going to do number 2. I will denote one big difference here because we know the relationships now between calories and joules. Up here, we had some information about water, right? And I told you guys to remember the specific heat capacity of water. What was the specific heat capacity of water? That's for the heat of vaporization of water. 4.18. It's literally the same number that we just used for calorie, okay? 4.184, but 4.18 joules per gram degree C. This is for liquid water. We will use that a whole lot, okay? So that's one that you'll maybe accidentally memorize. But we like to use joules because it's a version of heat, but so are calories. So notice in number 2, it provides you the C value within calories, not in joules. So we're going to run through this one together. We're going to set up that table like we did with C, M, and M, delta T, and delta T, where we have 2 of each of the variables. Ready? Okay. So a block of metal, C values that is heated to 88.2 degrees Celsius and then dropped into 100 grams of water, initially at 226.4. The final temperature of the water in the metal is 32.4 with the mass of the block. Okay? So remember, you may not remember, but in the video we mentioned going from system to surrounding. So heat exchange between one part and another part. So if we had to draw this, we'd have some water, and we'd have it starting off as what temperature?
6.4.
Okay, it tells us the starting point of water is 26.4. And we drop a piece of metal in there, right? That metal, is it hot or cold? Pretty hot, right? So it's starting off at what?
88.2.
Okay, so we're starting off by dropping this hot metal in here with a T initial of 88.2. Well, you guys are smart. You don't have to read the question. What's going to happen between the metal and the water? Corbin? Well, who's going to give the heat? Who's going to take the heat?
The metal is going to give the heat, the water is going to take the heat.
All right, so the metal is going to just give off heat, right? So it's going to be, is in the process of giving off heat. Are you trying to tell me that's a positive Q or a negative Q associated with the metal? Negative. It's losing heat, right? So that's what you have to think about in a question. Who's losing the energy? Who's gaining the energy? So the metal is definitely hot. It's going to have to come to thermal equilibrium. It's going to lose that extra energy and give it to water. So the Q of metal would be negative, but upon the water gaining heat or energy, we would denote a positive Q of water. But what's the relationship between both of these Q values? One is, this one's gaining energy, this one's losing energy, but what's the relationship between both of those? Say again? They're the same value, right? They're literally the same thing. These two things are equal to each other. So that's why we said Q equals to Q, or negative Q is equal to positive Q, because of the nature of how calorimetry works. And what law are we trying to indicate here when we set them equal to each other? Law of conservation of energy, right? So that's the concept behind calorimetry. Energy is not lost or gained, it's just transferred. And this transfer is occurring between the metal and the water. Okay, so now that we understand the background of that question, we can then write down the variables provided. So now we have metal and we have water. What data is provided for metal? What's the mass of metal? That's the question, okay? What's the mass of water? Okay, it says 100 grams of water, right? I also could give that to you as 100 milliliters of water, because what's the density of water? 1 gram per 1 milliliter, so don't forget, like I could give you milliliters occasionally. Notice it's going to be the same number. Okay, what's the C of metal? No, we don't. We can still use it. We totally can use that number. Let's use it as it is, and then we'll consider how to write water. I'm not going to convert unless I have to. Is that grams? Okay, good. Or is that a 9? That's a 9. So 0.30329 calories per gram degree C. Okay? Noting that information is in calories, you guys with me? What should be the C of water? Okay, so we want to say what? Go ahead and say it. Well, hold on. What we want to say 4.18 joules per gram degree Celsius, because that's the C of water I just told you to memorize. But this is in calories. So what's it got to be? 1, because 1 joule or 1 calorie is equal to 4.184 joules. So that C of water is 1 calorie per gram degree Celsius. All right, and then delta T. What was the temperature final for both of these? This is on your paper because mine's scrolling. 32.4, and that's going to be the final, right? T final minus T initial is what we're doing. So what was it, 32.4 or 34.2? Okay, 32.4 degrees Celsius, 32.4 degrees Celsius. What was the metal's initial? 88.2 degrees Celsius. What's this delta T, guys? Somebody calculate. I know you've already done it. 55.8. Okay, so that is a negative because, again, it lost energy. So we're showing that by a negative sign. And then the other one was starting off at 26.4. What is it? Oh, 6 degrees Celsius. And that's a positive value because what happened to water? It gained energy, hence the thermometer would raise the temperature. Okay, so some of you guys are going to be ahead, but if you wish, you can go ahead and move on to the next question. But I would like to give a straight follow through of this. So if you're sitting there pretty, do something productive if you like. Okay, from all these variables, there must be a more complicated equation we can use, right? Well, we know Q equals Q, because Q of metal is equal to the literal value of the Q of water. Which of these was negative? The metal, because it lost energy, so we need to identify that. But Q is not here, so instead we plug in for Q what? What is Q? What does Q just automatically equal based on what we talked about previously? MCAT, right? So we're going to say MCAT equals MCAT. So negative MCAT of the metal is equal to positive MCAT of the water. Because the Q equals Q, therefore the MCAT equals MCAT. Then we just very basically identify metal versus water so we don't plug the incorrect information in on one side or the other. So I'm a big fan of rearranging equations before I plug numbers in, because if I plug numbers in now, I'm going to screw up someplace and then I won't catch myself. So let's go ahead and do that just to satisfy me. So if we're looking for M of metal, what needs to be rearranged here? Divide by what? Divide by, I'm going to buy negative cat. So negative C delta T of the metal, divide by negative C delta T of the metal. So that hits M by itself now. So the C cancels, and the delta T cancels, and the negative cancels. So the mass of the metal will then be solved by doing MCAT of water over negative cat of metal. So that's what we're going to do. It's very helpful to label water and metal so you don't forget who is who. All right, I'm going to ask for you guys to start plugging in there because I need a little space here. That does not help me here. The M of water was 100 grams. The C of water was 1 calorie per gram degree C. The C of water was 6.0 degrees Celsius. All of that over negative, what was it, 0.0329 calories per gram degree C. And I think it was negative 55 point what? I was right there, 8 degrees Celsius. Woo! It's a loaded equation, right? But we've experienced this before, especially with gases. But if your units are there, it makes you happy because then you can verify you're correct. So the negatives I see here, I'm canceling out both negatives because like we said, maybe I didn't say something about that video, but you usually will never have a negative answer, period, unless you're talking about delta T, because technically delta T can decrease in temperature, so it can be negative. But mass will never be negative. Specific heat capacity will never be negative. And then our calories, our grams cancel, our Celsius cancels, our Celsius here cancels, and then our calories bottom and top cancel, leaving us with these grams. And by the process of inversion or copy dot flop or whatever you call this for yourself, this gram is going to be our final unit. What's that mass, guys? 326 is what I heard. Like 8 what?
39.
Okay, and then how many sig figs should this have? How many sig figs? It's really close to 3. So I know you see 3 all the way through, except for like there's a 4 one over there. When you subtract here, how many sig figs do you end up with? 2. So this actually is our controlling force. So that should be 330. Woo! All right, that whole application is in respect to the law of conservation of energy, which is calorimetry. All right, make sure that little box in your phone will complete, and then finish processing with a friend if you need to. We have one more big question. It's big, so you'll have paper for this. Actually, I might have you guys do one more of these to make sure you're good. Choose 3, 4, or 5 to set up at your table. Collectively choose 3, 4, or 5 to set up at your table. This is just for everyone one more time. 3, 4, 3, 4, or 5. Set up at your table.
remember I told you that sometimes you have to find the data point because it's not ASCII. .902. That's in joules per gram.
Yeah. Who's raising your hand if you're doing 5? Just this table. Raise your hand if you're doing 3.
What version are you doing 2? I mean 4. 4.
Okay. I think that's it. Yeah. Yeah, so that's working. I'll have you guys come to class. No, the initial temperature is 100. Remember, they both always end at the same temperature because that's when they're done exchanging energy. They got the thermal equilibrium. So what's the final temperature for both? Yeah. All right, give me a thumbs up once you've gotten set up and you've processed and you feel good. You feel where you know how to calculate this one. All right, take about 30 more seconds wherever you are. I want to talk to you about number 5 on interpretation. I would go ahead and write down the interpretation for 5. Write down the MCAT on both sides. right, come back to me. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I want to make sure you can interpret 5, but I think I'm going to give you some guidance here, okay? So, reading 5. What is the mass of a block of aluminum that was boiled in water and when placed into a calorimeter raised the temperature of 125 mils of water in a calorimeter from 22 to 23.6 degrees Celsius? Okay, so let's visualize what's happening here. Where's the metal starting off at, like physically in the lab? It is starting off in some boiling water. So we have a hot plate, the water's boiling. What's the boiling point of water, guys? 100 degrees Celsius. So we pop that metal in there, and the metal is going to heat up to what temperature? No, this is before the lab, before you even start doing heat exchange. This is the first sentence. Mass of aluminum that was boiled in water. What should this metal heat up to? Come on. It should initially, the TI of the metal, the initial temperature of the hot metal should be 100 degrees Celsius. This is not the water in the calorimeter, hence this is not the initial temperature of the water. We don't even record the water of this scenario. This was just the media we used to heat the metal up, because, I mean, how else can we heat a metal up?
Miss Enlow, could we get Riley for dismissal?
Yes, ma'am, thank you.
Thank you.
Finish watching the video, sir. So basically, you're not going to put a metal in the microwave to heat it up. So we're heating on some hot water. Okay. So then we take this and we put it in a coffee cup calorimeter. Well, what's in the coffee cup calorimeter already?
Water.
Water at what temperature?
22 degrees Celsius.
22 degrees Celsius. And so when we put that hot metal in there, everybody with me? That back table specifically? Thank you. You put the hot metal in here, what happens? What does it say happens? Raise the temperature of the water to what? And remember, our temperature final for the metal and the water are always the same because they always stop changing temperature at, what's the term? Thermal equilibrium, thank you. So that's going to be our T final for both, whereas the initial temperature of water is 22, the initial temperature of metal is 100. And I think after that, everything else is good in terms of interpretation. Are we okay on the rest of that? Okay, I just wanted to show you that one because sometimes you'll mix up the temperatures. Okay, quick stretch break. Get up and talk about what you did this weekend. Quick stretch break. This is your opportunity. Or what you're doing for next weekend. Who has seen Avengers Infinity War?
But you always have to wait like 10 minutes for credits for so long. I know. Oh my God.
All right, and come back to me. 3. Awesome. Okay, so last type of question we're going to talk about today, okay, is the heat of phase change. So that's the third, wherever you put your third foldable information. And that was the one, let me actually go back to that slide you guys wrote down information from here. That's where you guys wrote down a kind of a new equation, Q is equal to moles, right? This is the first time we've seen mole, times delta H. Delta H comes in 2 flavors. Heat of what? Fusion, which what process is that referring to in a physical process change? Physical change process? Solid. Right, that just literally is a fancy word for melting. Okay, so if you need to add that to your identification of what fusion is, that's a fancy word for melting. What's vaporization refer to? Liquid to gas, so hence vaporization or boiling kind of thing. Okay, So what we're doing now is we're actually going back to heat curves. So on that first reading you guys had, does cold exist? Does cold exist? No. So when someone says, I'm cold, what do you say to them? Well, can you explain more? Right? If they say I'm cold, you say no, you're just lacking.
Heat.
No, what's a better? What kind of kinetic energy? You just have some low kinetic energy up in you, right? So you're just there's a low kinetic energy system around you. Don't whine about being cold. Okay, so draw a heat curve for me in the air. Heat curve. Okay, so you have this nice. I saw it look like this. Da 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 da. Right. What's happening? What are the axes? What's this axis over here? Okay, I'm going to put degrees Celsius to represent temperature down here. Time or energy. I'm going to put heat since that's the energy type that we're kind of referring to here. Okay, so where does temperature not change? The plateau. Haha, right here. So what are these representing? Both of these are representing phase changes. You guys already have a picture in your... Okay, so this is pretty much what you're describing. So on these parts of the graph, on the slanted part here, and here, and here, we obviously have a change in temperature, right? So if I were to calculate the heat applied to force the temperature to change, what equation would be used on these green sections? Okay, let me rephrase that. I'm calculating the heat from a temperature change. Q equals MCAT, because I have a temperature change and I'm calculating heat. That's the only equation where temperature change and heat come into play together. So that would apply to here, here, and here. Well, dang it, I can't use that equation on the plateaus because there's no way. Because if I multiply anything by 0 change in temperature, what's the heat going to be? 0, and that's totally not correct because you can definitely see there's heat applied over the process of this phase change occurring. So this must use a different equation. Which one?
Q equals moles.
Q is equal to moles times the specific delta H. So this is delta H of, what process is this? Fusion, because we have a melting process or a solid to liquid process occurring in this first phase change. And the second one is delta H of vaporization because we're going from liquid to vapor, or liquid to gas. So what we're going to do is we're going to process one big, huge heat curve. We're going to calculate baby steps. Calculate the heat applied to make the temperature change. Calculate the heat applied to melt. Calculate the heat to make temperature change. Calculate the heat to melt. Calculate the heat to temperature change. So how many Q's is that? How many Q's is that? 1, 2, 3, 4, 5. 5 Q's. Here we go. Ready? Yeah, we're about to do this right now. All right, I'm moving on. So we're going to go ahead and do this. So we are. Dang it, where did I copy that? We're here. Right. This is the third section on your sheet. Let's do number 4. Only because if you can do 4, you can do the rest of them. There's one specific piece of information that we'll use, which are these values here. Do you recognize this one? Yeah. Right. I sometimes use the 6 or the 4, but if you just put 4.18, it'll be fine. That's the more specific version of the specific heat of liquid water. What you should write down is the specific heat of ice, like solid water, versus the specific heat of vapor water or steam. You'll notice they're different, so we just have to respect the state of matter. We have to suggest the correct specific heat value. So we will need those, so write those down someplace. I'm going to ask you for a lot of help here, a lot of values, so work with me. All right, 205, 4.18, 202. And give me a thumbs up when I'm good. Okay, so I'm going to point out a big deal here on number 4. How much heat is required to change 52.9 grams of ice at -15 into steam at 230 degrees Celsius? It's telling you you're going from ice to steam. So you have to draw a heat curve to really understand every single step it takes to get from ice to steam. So on that heat curve, we're going to label everything we know, and we're going to calculate from the heat curve. And I'm going back to get a blank slide. And where's that question? That's question 3. No, this is question 4. This is the same question 4 in your paper, right? That, okay, I just mislabeled it. This is number 4. Okay, so we have a heat curve. Draw yourself a heat curve, and let's label each part that that we know. I draw it kind of big just so you can label things really well, and you're not trying to squeeze information on there and you can't see it. All right, so for this scenario, where are we starting? What temperature?
Negative 15.
Thank you. So negative 15. I'm going to start us way down here at negative 15 degrees Celsius, and that's our ice. Well, ice is going to remain ice until it hits what temperature? 0 degrees Celsius, which is our temperature that ice, or aka water, melts. So it's going to be ice, 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 and it's going to hit the plateau, and that temperature is going to be what? 0 degrees Celsius. So this graph now is going to allow us to determine our what?
Change of temperature.
Delta T, right? We're just literally reading the graph. We know what delta T now. But before we start calculating, it's going to be changing to liquid here. I'm going to put delta H fuzz just for fusion to indicate I will need that in a second. And then it's going to be liquid all the way up until what temperature? Right, we all know water boils at 100, and this is assuming atmospheric conditions of 1. So that's going to be 100. Okay, and then it's going to melt or vaporize, delta H vap, and it's going to be heated from 100 all the way up to what, according to this question?
230.
230 is our peak up here. There we go. So now that we understand the graph, we understand what things we can pull graphically, now we can start calculating itself. So I want us to calculate each of these Q's for this temperature change, for this temperature change, and for this temperature change. Let's do those first, okay? So I'm going to call this Q1, I'm going to call this Q3, I'm going to call this Q5, just because it's 1, 2, 3, 4, 5, okay? So Q1, what's some space here? Q1, what equation applies when temperature is changing? MCAT, right? So Q equals MCAT. What's the mass of this substance?
52.9 grams.
Okay, so Q1 is equal to 52.9 grams. What's the specific heat capacity in this section of the graph? Say again? No, what's the specific, like, okay, what state of matter is this right here? This is solid ice, right? What's the specific heat capacity for ice? 2.85 joules per gram degree Celsius. So I just need a little bit more space. We are gonna drag this down here. Okie dokie. All right, so this is 2.05 joules per gram degree Celsius, because that's what you guys wrote down just a minute ago, because that is ice. What's delta T here? So remember, we're doing T final minus T initial. What's T final here? 0. What's the T initial? So we're subtracting a negative. So what is that? Positive 15, right? Because a negative and negative is positive. So I need some calculators here. Everybody should calculate so I can get an answer. I'm moving on. $52.9 times 205, 2.05 times 15.
162.
Say again. 1626 point. I'll just go like that. Okay, so that's joules. So Q1, maybe box that answer so you don't lose it, because we're going to have a lot of work here, okay? So that's Q1, and that's the first temperature change. You are going to repeat this process to calculate. We've done Q1. You're going to calculate Q3 and Q5 at your tables. Go. Talk it out a little bit if somebody needs some help.
Will the C would be
And what's different in this particular one? And what else is different for this? Yeah, so the mass is the only thing that stays the same. Calculator, right? Check my work for me. Are we done? Okay, no, we're not done with the problem, but are we done with the three calculations? Okay, so at this point, we're like, okay, yeah, we got all the temperature changes taken care of. I know like how much energy it takes to change that temperature fully from -15 to 230, but I've not calculated the heat it requires to phase change. So that's our heat of fusion and heat of vaporization. I had you guys write down two values on your foldable. Do you guys remember those or look at your foldable? For water, what was the delta H fusion? 6.01 kilojoules. Okay, well that's a little different, right? So we got to recognize that per mole. Okay, so we write that down on the front of our foldable, and this is again for water. Every other substance would have different values. So we use water a lot in our samples, so you'll see these. What was the delta H vat for water? How did you guys write on 40.1? I may have slightly made those up, but they are very close to what they should be. So I was doing this from memory on that video. So if you look up something else, I think it's like 40.6, but whatever, we're going to use those. Okay. All right, so we've got fusion and vaporization. What equations do we have to use with that? Moles times delta H or whatever, right? I do want to use the mole one. We did reference in the video like a joules per gram one, but I just want to show you another route here. So we're going to call this Q what and Q what up here. Q2 for the fusion and Q4 for the vaporization. Let's roll, okay? So Q2, let's do that one first. So Q2 is equal to moles of water times delta H of fusion. I don't even care if you literally calculate the moles. You can just write the process down. So what are we starting off with to get moles of water? 50. Good. So 52.9 grams of water. What's water's molar mass, guys? Approximately about 18. Okay, so 1 mole of water divided by 18 is going to give us our molar mass. Okay, so I'm just going to leave it like that because I don't really care what the number is, but unless you want to tell me, what's the number? What is this? Say again? I heard 3.93. Oh, 2.93. Okay, so that's our moles of water. We're going to multiply that by the fusion, which was 6.01 kilojoules per mole. All right, what unit cancels here? mole and kilojoules is left remaining. What is Q2 in terms of kilojoules? What's 2.94 times 6.01?
17.6.
Okay, and that's kilojoules, right? Okay, I want to just see if you guys know or think about what we're going to have to do eventually here. Any thoughts here? Yeah, if we're messing with joules with all these other numbers, we need to have a consistent unit. So let's go ahead and do it. Let's convert this to joules. How do I convert kilojoules to joules? Say again? 1 kilojoule is equal to 1,000 joules. So 1 kilojoule is equal to 1,000 joules. So how many joules is that? A lot, right? 17,669 joules. Okay, that's Q2. Thank you for your patience. We got one more to do. So that was the melting phase. Now we're going to do the what? Say again? The vaporization phase. So we're going to grab 40.1 from up here. Okay. So Q4 is moles times delta H vap. Right? What were the moles? We already calculated this. 2.94 moles. What's heat of vaporization? 40.1 kilojoules per mole. Moles cancels. Good. And then what's that value, guys? 117.894 kilojoules. And then we see kilojoules, we're like, nah, moving on. What are we right here? I can't work with kilojoules if everything else is in joules, so all right, I need to cancel that out, right? So I need to convert 1 kilojoule, using 1 kilojoule and 1,000 joules. Oh gosh, 117.894 joules. And that's Q4. All right, is our process complete? It's super, super close, right? What was this question? What was the whole question? How much heat? All right, so do we know how much heat? Just add them up. Yeah. Oh my. So we know 5 steps worth of heat, and now we're adding the 5 steps up. So I'm going to scroll back to the top and start highlighting the stuff I need to add, but you guys have it on paper. Q1, 1626.67 plus 2212.2 plus 13,891.5 plus 17,669 plus 117,894. All right, compare with the person next to you. What'd you get, Bailey? 17. Is this close? Is this close? Okay. And I'm going to round that to 173 kilojoules. Approximately. Q total. Okay, well, I know your brain's hurting for a hot second, but grab your laptops, and then I'll take a poll again to see where we are. Grab your laptops. Okay, guys, so on a scale of 1 to 10, that first flop of the focal, just Q equals MCAT stuff. Scale of 1 to 10, throw your hands up. I gotta know. It's a survey. Participate. Okay. On a Q equals Q setting, so the calorimetry, where you have a lot of variables, interpreting the questions, and using that. Keep going. Give me a 1 out of 10. Those are a little bit more challenging. I get it, because you have to really sit and like interpret the question. Okay, combining Q equals MCAT with phase changes, like we did on this heat curve. Okay, is it challenging, like it's just tedious, or it's like, I don't understand? It's tedious. I think a lot of you are saying it's tedious, but we'll do another example. I'm not going to do another example right now, because it's going to take me the rest of the class, and I just don't got it. Don't got it in me right now, okay? But if you ever see something that makes you go from... If you ever see something that makes you go from one state of matter to another state of matter, and you notice a huge temperature change, draw a heat curve, and it'll help you a whole lot in understanding the steps it takes. Alrighty? Okay, so we're going to go to my website when you get a chance, but I'm going to show you from up here what's expected. Who's ever done some sort of like fit or a calorie tracker or food tracker or energy consumption tracker in their life? Or who's ever seen one? Okay, so literally what you're going to do is you're going to understand how your real life eating habits correlates to the energy consumption and energy burning that you have and that happens due to your metabolism in your body. So we're going to pull up Enlo's website and go to MyFitnessPal assignment. It is a 4-day tracker, so you have to track what you eat for 4 days. Okay, 1 day is maybe not really what you eat on a daily basis, because maybe you have a bunch of junk food one day or a bunch of candy one day, and then you're like fruits and vegetables the next day, right? So I want to see a general pattern, but when you pull up the link under Monday, this will come up. So I'll explain to you while you're getting there. And I put a couple of options, because some of them require you to be 18, but you sign up for what you sign up for, okay? So the assignment is a 4-day nutrition journal that will require you to keep a detailed log of everything you eat and drink. You can use the MyFitnessPal app, Lose It, there's a bunch of them. These are the top 5 supposed best free calorie counters. You can use whatever you want, but let me tell you what I expect in the end, so maybe you can make an informed decision. You're going to create an account. That created account will be new for today. If you already have one, of course, you could totally use what you already have. Maybe you've done it for another class before. But basically what I'm grading you on is right here. 10 points just for creating an account and getting engaged with us today, okay? 2, an accurate account of 10, it's 10 points a day, so 4 days total of breakfast, lunch, dinner, snacks, whatever. That's your second part of the rubric. And then the reflection, which is the very last page of this, is the other 50 points. So you get basically a 50 for just doing it, and then another 50% for reflecting on the process, okay? So as you can see, this may not come up with yours. The MyFitnessPal account does come up with this, and so you don't have to break it down by carbs, fat, and protein, nor do you have to track fitness like exercise, but if you want to, absolutely, that's on you. And then it tells you, this is the instructions on the mindset of MyFitnessPal, but of course other opportunities and other apps will give you similar instructions. But the reflection task is right here. This is the last 50 points. And this is all done after your 4th day. So basically, did they suggest the right amount of calories, too few, too little, or too few, too many? Were you able to meet your goals? What kind of insight have you now achieved? And then the most important question, really dig in, how does this relate to chemistry? Okay, so let's take 10. Let's make an account using any app or any website you opt for. I gave you some options on the top of this document. And then I would maybe go ahead and write down what you've had today. Maybe you've had nothing today. Well, that's an easy task for you, isn't it? Okay, so I gave you some options. If you would like to use your phone instead, you can download an app that will do it. Oh, sorry, the last thing. The 4 days, I won't know that you've tracked yourself, right? So you have to either screenshot it from your phone if you use an app on your phone, like the 4 days worth of food tracking, or from the MyFitnessPal website, they actually have a nice printout we can print out the end. That's again why I suggest this one, but it's up to you which opportunity you use. My Plate Calorie Counter is the other one.
You'll bring that with me, whatever it is in the end, we'll screenshot because if not, you won't have any way to track. Yeah, I don't care if you guys, this is a personal activity. You want to gain weight, you gain weight. You want to lose weight, you lose weight. You want to stay fat, you They're not that important. They're going to